When we're talking about gases, there are four basic properties or quantities that we measure. Pressure is important. We've been talking about pressure. We use capital P to stand for pressure. The volume of a gas is important. That's capital V. The temperature is important. That's capital T. And the amount of gas. We measure the amount in moles. And the amount is N. Does that seem strange to anybody else? We use M for so many things. I think it's like, okay, well, N is kind of like the M, so we'll use that. Anyway, those are our parameters. They are interrelated. If one changes, at least one other one has to change. And so we're going to talk about the simple gas laws, which describe relationships between pairs of these properties. So we'll look at just temperature and volume, or just pressure and volume, instead of looking at all four of them changing at once. So Boyle's law. This is Robert Boyle, and he lived back in the 1600s. Hey, that's a long time ago. America hadn't been discovered. No, it had been discovered. It wasn't a country. That was 1492. But we became a country in 1776. This is a long time before that. So that gives you an idea for how long ago this was. So Boyle and his colleague Hooke used a J tube to measure the volume of a sample of gas at different pressures. So this tube is shaped like a J. That's why it's called a J tube. And it's sealed off at this end. So they've got a gas in here, and they can tell the difference in pressure between outside and inside by looking at the difference in the height of the column of mercury. Then if you add more mercury, it's going to push down and compress the gas. The gas gets smaller, and the difference in pressure is greater. And so in this way, which is very simple, no technology here, they were able to look at the relationship between the pressure of a gas and its volume. If you think about balloons, balloons are probably the best thing that we can relate to in terms of gases. If you increase the pressure of a balloon, is it going to get bigger or smaller? It's going to get bigger, right? So they were able to look at a relationship between volume and pressure. Bless you. So they varied the pressure, measured in millimeters of mercury, and they measured the volume. And what they found was, at low pressure, it had high volume, and as the pressure increased, the volume decreased. This is called an inverse relationship. When one goes up, the other goes down. When the first one goes down, the second one goes up. They go opposite of each other. Inverse relationship. So this can be expressed as a proportionality. Volume is proportional to 1 over the pressure. If we look at this, if P gets larger, then 1 over P is smaller, and the volume must be smaller. Proportional just says there's a relationship, one goes up, one goes down. It doesn't say exactly what the relationship is. There's a constant involved. These are the simple gas laws. Here we're looking at volume and pressure only, which means we have to keep the temperature and the amount of gas constant. Well, keeping the amount of gas constant is easy. You keep it in a container, you don't add any, you don't let any out. The volume, the amount of gas is constant. And then you just need to keep it in a constant temperature. The graph of P versus V, pressure versus volume, is curved. Actually, that graph was volume versus pressure. If you take those numbers and graph 1 over V, or P versus 1 over V, or V versus 1 over P, what you end up with is a straight line. And I keep meaning to put an actual graph like that in here, and I keep forgetting. So the way proportionalities work is you can say that the volume, if it's proportional to 1 over p, it equals some constant divided by p. I'm sorry, that's not what I meant to write. Equals some constant. Then if you rearrange that, you get pressure times volume equals this constant. Well, if the constant is constant, which most constants are constant, then under one set of conditions, pressure times volume equals this constant, pressure 1 and volume 1. Then under a different set of pressure and volume, it must equal the same constant. And so we get this relationship right here, and this is what we refer to as Boyle's law. I will not test you in the midterm exams on which one is Boyle's law. I have a hard time remembering myself because there's a whole bunch of different simple gas laws, and they all have names. It could show up on the ACS final exam. It could. So just want to warn you about that. But what's important is that we know this. P1V1 equals P2V2. Pardon me? The American Chemical Society. Your final exam is the American Chemical Society standardized exam. Sounds scary. No, it's not scary. Well, let's look at what's going on with the molecules when we're thinking about Boyle's law. So here we have a volume of gas. It's 1 liter, and the pressure is 1 atmosphere. And we see there's a weight on here, putting pressure on the gas. If we double the weight, so that was 1 kilogram, this is 2 kilograms, so now the pressure is 2 atmospheres. We doubled the pressure, we cut the volume in half. As the volume of the gas sample is decreased, the molecules now are going to run into each other more frequently because they're being pushed together. And which of these containers has a larger surface area on the inside? The big one, right? So over here, the surface area is smaller, and we've got more collisions. The pressure has to go up. So we double the pressure, the volume gets cut in half. This has implications for scuba diving. For every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure because of the weight of the surrounding water. At 20 meters, the diver experiences approximately 3 atmospheres of pressure. That's 3 times the normal atmospheric pressure. Do any of you guys scuba dive? Yeah, okay. Anybody want to go scuba diving? It sounds kind of creepy to me. You know, I don't know, just being that far underwater, I don't know. So if a diver is down there at 20 feet, 3 atmospheres of pressure in his lungs, and he holds his breath and comes up to the surface really quickly, where the pressure is 1 atmosphere, what happens to the air in his lungs? It expands, right? So he went from 3 atmospheres to 1. The pressure dropped by a factor of 3. The volume of gas in your lungs would increase by a factor of 3. Would that be good? No. There are reasons that they make you. You had to take a whole bunch of classes, right, before you could go? Yeah, hours of instruction. Because you could just kill yourself so easily scuba diving and not knowing what you're doing. You have to exhale. Exhale. Yeah, it also definitely the air in your blood and nitrogen solubility in your blood and all kinds of stuff. But you got to exhale so that the pressure can change as the volume changes. Always exhale. So let's look at an example. So we've got Boyle's law, and we're going to do calculations. So I'll write it up here in case you've forgotten it. P1 V1 equals P2 V2. It's a lot like that dilution equation. Boyle's apprentice finds that the air trapped in a J-tube occupies 24.8 cubic centimeters at 1.12 atmospheres. By adding mercury to the tube, he increases the pressure on the trapped air to 2.64 atmospheres. Assuming constant temperature, what is the new volume of air in liters? So gas law problems are almost always going to be word problems. And there's going to be multiple numbers, and we have to put them together in the right way. The actual math and algebra is pretty simple, but we need to organize this stuff. So what I find works really well is to make a table. These simple gas laws, we're going to have changing conditions. And so let's make a table for condition 1 and condition 2 and write stuff down. And I'm going to start over because that's way too big and I'm not going to have room for what I need to do. Let's try that again. One and two. And so you read through the whole question and then go back and pick out the numbers. The first number is 24.8. So I'm going to write that in here, 24.8 cubic centimeters. And then I say to myself, what does cubic centimeters measure? Volume. So I'm going to give this column the heading V for volume. And the next one is 1.12 atmospheres. And those two seem to go together, right? It's this volume at 1.12. So 1.12 atmospheres. Atmospheres measures what? Pressure. So this is going to be P. He's adding mercury to the tube, okay. 2.64 atmospheres. Well, I want to put that in the pressure column. 2.64 atmospheres. And now I'm out of numbers. What's the question? What is the new volume? Well, conveniently, I have one blank in my table, and it's a volume. So I'm going to call that V2. So this is V1, P1, this is V2, and P2. And here's our equation, and we are going to solve for V2. So this does require a little bit of algebra. So P1 V1 equals P2 V2. So we need to get V2 by itself. It's multiplied by P2. If we divide by P2, they will cancel out. And I need to do the same thing to both sides for them to stay equal. Be careful when you're copying these things down because it's so easy to exchange the ones and twos and then the answer will be wrong. So V2 equals P1 V1 over P2. There are other ways to do these problems, but this seems to work for most students. So there I've got my equation. If you need help rearranging equations, if algebra is a mystery to you, please come and talk to me. I can help you with that. But I don't want to bore the people who get it. So now we're just going to pull the numbers out of the table. Always write your units. Write the units in the table, write the units in the equation, and make sure that they work out the way they're supposed to. So pressure 1 is 1.12 atmospheres, and volume 1 is 24.8 cubic centimeters, and that's all divided by volume 2, which is not volume 2, pressure 2, 2.64 atmospheres. And then we look at the units. Atmospheres cancel out. And then we get out our calculators. And we calculate. 1.12 times 2. Times 24.8 divided by 2.64, and I'm getting 10.5. That would be 3 sig figs, right? And what's the unit? Centimeters cubed. Would mastering chemistry like that as an answer? No, because it says liters. Any questions about how I got this? Now we just need to convert this into liters. A cubic centimeter is the same as what? A milliliter. So I can just cross that off and write milliliters, and now this is so much easier to convert. Milliliters on the bottom, liters on the top. Milli means 10 to the minus 3. And so this is going to be 1.05 times 10 to the minus 2 liters. Any questions? With the simple gas laws, you can look at the answer and say, is this reasonable? So here's my initial volume. The pressure was increased. I'm putting pressure on the balloon. Do I expect it to get bigger or smaller? I'm putting pressure on it, squeezing it. You expect it to get smaller. And did it? Yeah. When you put pressure on a gas, it gets smaller. Any questions? Charles' law. Charles' law relates volume in temperature. And so this was later, 1746 to 1823 is when J.A.C. Charles lived. And he looked at the relationship between gas volume and temperature. And he found that the volume of a gas is directly proportional to its absolute temperature. This is why we need the temperature scale of Kelvin, the Kelvin temperature scale. So Charles' law says that the volume is directly proportional to the temperature. That means if the temperature goes up, the volume goes up. And this is assuming that the pressure and the amount of gas is constant. Think about a balloon. When you heat a balloon, does it get bigger or smaller? It gets bigger. And if you cool it down, it gets smaller. And that's something you can try at home. You can kind of blow up a balloon middling size and stick it in boiling water and watch it get big, and stick it in ice water and watch it get really, really small. So volume proportional to temperature leads to volume divided by temperature is equal to a constant, and so we get V1 over T1 equals V2 over T2. And this is the usual expression of Charles' law. This is super important. It has to be in kelvins. It will not work in degrees Celsius. Okay, and then the conversion between Celsius and Kelvin is adding. It's not multiplying or dividing, and so it's not going to cancel out. The thing about Kelvin temperatures is that they can never be lower than 0. You can never have a negative temperature. If you put Celsius in here and you have a negative temperature, then one of those volumes may end up being negative. Can you have negative volume? No. No, you can't. Okay. This is a graph of volume versus temperature. So they changed the temperature, they measured the volume. And what they found was for different amounts of gas, so here's 0.25 moles of gas at 1 atmosphere, and 0.5 moles of gas at 1 atmosphere, and 1 mole of gas at 1 atmosphere. They made these nice straight lines, and if you extrapolate the lines, they all intersect at the same point. As the temperature decreases, the volume decreases. And you get to this point where the volume is zero. And that's absolute zero. Can the volume of a gas get smaller than zero? No. That is the theoretical lowest temperature. It's called absolute zero. So that is where the minus 273.15 came from. It's where those lines intersect. And this has been done many, many times, and it always intersects at the same place. Here's pictures of what happens if you do the ice water, boiling water thing with the balloon. Low kinetic energy. Remember, temperature is a measure of the average kinetic energy of the particles. People walking on the sand, right? Cold sand, barefoot people walking slowly. Hot sand, barefoot people running to get off the hot sand, right? So here we have slow gas molecules, and they have low kinetic energy. They're not going to run into the walls as frequently or as hard, and so the pressure is going to be lower. High temperature, high kinetic energy, they're running around like crazy. They're hitting the walls harder and more frequently, so the pressure is greater. It really helps if you can think about, well, what are the particles doing? In high temperature, they're going faster, and you can kind of reason it out that way. It really helps. Question? Why is it shaking? That's a good question. So I said this part. When the temperature increases, gas particles move faster, collisions are more frequent, the force exerted for each collision is greater. The only way for the pressure to be constant, pressure is force per unit area, there's more force now, is for the gas to occupy a larger volume so that the collisions become less frequent and occur over a larger area. So if the temperature increases at constant pressure, the volume has to go up as well. Hot air balloon. Hot air balloons are cool. No, they're hot. The air's hot. Sorry, it's getting late, isn't it? Regular balloons have to be tied off, right, or the air comes out. Hot air balloons are open at the bottom, and yet they fill up. That always kind of just mystified me as a child. Well, what happens is you've got this ginormous burner here, putting out lots of heat, and it heats the air. And what happens when you heat air? It rises and it expands. It rises because it has expanded. Its density is less when it expands. And so what happens is the gas is rising and expanding, and so it fills up the balloon. And it keeps expanding as it gets warmer and warmer, and the more it expands, the lower the density, and a lower density gas will float in a higher density gas. That's why a helium balloon floats in air. A balloon that you blow up with air is just not going to float. I don't care what they do in the cartoons. It's not going to work that way. And this one, I am not exactly sure why that's there. I think this is a Dewar flask of liquid nitrogen with the balloon in there, but I don't remember. It got really small. Yeah. Okay, it is liquid nitrogen. So I take a regular big balloon and stick it in liquid nitrogen, which is really, really cold. That's what they use to freeze warts at the doctor's office. And it'll get really, really small as it cools down. I've never had warts. It's my kids. Right? Okay, let's do a Charles' law problem. So Charles' law, V1 over T1 equals V2 over T2. That's a 2 out of 3. A sample of sulfur hexafluoride gas occupies 9.10 liters at 198 degrees Celsius. Assuming that the pressure remains constant, what temperature in degrees Celsius is needed to reduce the volume to 2.50 liters. Okay, so this is a gas law problem. We've got something changing. We've got a gas here, and so we're going to make a table. We're going to just go through and write down the numbers as we come to them. 9.10 liters. Now let's try that again. 9.10, that's a little better. Liters. Liters measures what quantity, volume, thank you. At 198 degrees Celsius. 198 degrees, that is temperature, right? What is wrong with that temperature? It's in Celsius. Change it now. Do it now, because you'll forget later. You'll get all calculating happy and you'll forget. So as soon as you write it down, change it. So 198 plus, oh my goodness, shouldn't be so hard, plus 273.15, 471.15. Kelvin. Now, if we're thinking about significant figures, where is the uncertain digit in that one? It's right here in the ones place, right? We were adding something, and this has uncertainty in the ones place, and so this number also uncertainty in the ones place. Go ahead and keep the 1.5. It can just come along for the ride. Assuming the pressure remains constant, what temperature in Celsius to reduce the volume? There's our number, 2.50 liters. We have one empty box, and so we're going to call that T2. Now we need to take our equation and rearrange it. V1 over T1 equals V2 over T2. This equation has fractions in it. Get rid of the fractions first, because we are solving for something that's in the denominator. And I don't know what they teach you guys in your math classes, but people lose their minds and they end up solving for 1 over t and they don't see any problem with it. And it's not a good place to go. So let's just get rid of the fraction and then we'll completely avoid that problem. How do we clear fractions? Cross multiply. We're going to cross multiply and get rid of the fraction. So we're going to take these two things and those two things. And so we're going to have V1 T2 is equal to T1 V2. Okay? Cross multiply, it's really the best thing. And you should not do that. There we go. You should do your rearranging with the letters. Don't put the numbers in and then start messing around. I let students do that one year, one semester, and it was a really bad idea. Bad things happen. It's much simpler to rearrange things when it's just the letters. So we want T2. So now we can see that we need to divide by V1. These guys cancel out. And so we have T2 is equal to T1 V2 over V1. So T1 is 471.15 Kelvin. Write the units in there. Volume 2 is 2.50 liters. Volume 1 is 9.10 liters. We see that the liters cancel out. That's good. And we're going to end up with a temperature in kelvins. Uh, 471.15 times 2.5 divided by 9.1. How many significant figures should our answer have? 3. 129.44 kelvins Should have 3 sig figs. I'm not rounding that yet because we need to find the temperature in Celsius. And so we need to subtract 273.15. And now we'll round to 3 significant figures, and we're going to get minus 144 degrees Celsius. Is that a reasonable answer? We are reducing the volume. To make the volume smaller, do we need to heat it up or cool it down? We need to cool it down. And so it went from 198 degrees Celsius to minus 144 degrees Celsius. That's the right direction. If the units work out, the most common mistake is that you've got your 1s and 2s backwards, and it'll go in the wrong direction. And then you can catch it by looking at it. Any questions? This is not the only way to do these gas law problems using algebra. There is a different method using ratios and just kind of thinking about it, and oh, it must go up, and so I'm going to multiply by a ratio so that it goes up. And that's a great method too. Students tend to have a harder time understanding that. And most students that do understand that, understand it whether I teach it to them or not. So if you're doing it that way, just keep on doing it that way. You're good. Avogadro's law. Amadeo Avogadro. He was born in 1776. So he was the first one to formally state the relationship between volume and amount of gas. So Avogadro's law relates volume and moles. It turns out that volume is proportional to the number of gas molecules. And that kind of makes sense, doesn't it? If you put more gas in, you're going to expect the volume to get larger, right? But what wasn't really obvious is that it is a direct proportion. If you double the number of moles, you double the volume. So this is the expression of Avogadro's law, which looks a bit like Charles' law, but with N instead of T. N is the number of moles. It's not the mass. It doesn't depend on the mass. It depends on the particles. And that's one thing that makes working with gases very different. So equal volumes of gases contain equal numbers of molecules. What the gas is doesn't matter. And some students find this a little disturbing. If I have 2 balloons, same volume, same temperature, same pressure, they will have the same number of moles of gas, even if one is argon and one is helium. One's a really big atom and one's a really small atom. The reason that is because in a gas there's so much empty space that the actual size of the gas particles doesn't matter at all. Here is a graph of Avogadro's law. So if we increase the number of moles of gas, the volume increases in a linear fashion. And if we extrapolate, we find that it predicts that at 0 moles, the volume would be 0. Yeah. Like, well, duh. Right? Let's do a calculation with Avogadro's law. A scale model of a blimp rises when it is filled with helium to a volume of 55.0 cubic decimeters. When 1.10 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant T and P. Well, obviously this is a gas law problem. Now we've got three different equations, and of course we just talked about Avogadro's law, so this is probably going to be an Avogadro's law problem, right? But on an exam, they'll be all mixed up, and sometimes students have a hard time figuring out which gas law they should use. Well, you don't have to decide right away. Just make your table, and the table will tell you what to do. So let's make a table. Ones and twos. So volume of 55.0 cubic decimeters. That's not a unit we see very much, but it's fine. 1.1 mole of helium is added to the blimp. Okay. So we think about that, and we're like, that sounds a little funny. Let's skip that for now. Volume is 26.2 cubic decimeters. We know what to do with that. That's a volume. We'll put it in the volume column. Okay, so let's think about what this problem is saying. This is a tricky problem. This is not a straightforward problem. So the blimp, when it's filled to this volume, will float. This is the other volume that we have. Is that going to float? No. When 1.1 mole of helium is added to the blimp. So this must be that we partially filled up the blimp, right? We put some gas in, but it's not enough to float yet. So this 1.1 moles of helium must go with this smaller volume, 1.10 moles. So that's N. And then they're saying how many more grams of helium must be added to make it rise. And we think, ooh, that sounds icky. Hey, look at the table. Look at that. There's a blank here. I could solve for that. That works. Let's do that and then see if we can figure out what to do with the rest of it. This is a problem that I would expect to be challenging for a lot of students. This requires you to think and not just to plug numbers into an equation. But we could calculate N1. So let's figure out what N1 is. Well, when you have something like this, and like on an actual exam where it's not under the heading of Avogadro's law, look at what kind of things you've got here. You've got N, and you've got V, and you've got 1 and 2. Okay, we need the equation that has V1 and V2 and N1 and N2. And at this point, you'll probably just go look in the book or in your notes and see what it is. Before the chapter's over, I'll show you how you can figure all of these out relatively simply. So right now what we've got is Avogadro's law, V1 over N1 equals V2 over N2. And we have that whole fraction situation going on again. So let's cross multiply, get rid of the fractions. So I get N1 V2 equals, running out of space, N2 V1. And then I want N1 by itself, so I'm going to divide by V2. Have to do it on both sides. So N1 equals N2 times V1 divided by V2. N2 is 1.10 moles. That's not going to fit, is it? moles. V1 is 55 cubic decimeters. V2 is 26.2 cubic decimeters. Nice, the cubic decimeters canceled out. We don't have to do anything with them. 1.10 times 55 divided by 26.2. Well, I have space up there. I'll write the answer up there. 2.30916 moles. That one should have 3 significant figures, but this was kind of a confusing problem, and so we're not sure if we're done yet. Well, yes, it's asking for grams, but this unit is moles, right? So what is this? What does this mean, 2.3 moles? This is the number of moles of gas that needs to be in the blimp for it to float, right? How many do we have in there right now? 1.1. How many moles of gas do we need to add? The difference, right? So we need 2.30916, and we have 1.1. So the difference between that is 2.20916. Yes. I can't even pick up an eraser. Thank you. And that's moles. Those moles need to be added. But the question wants to know mass in grams. Periodic table. Let's throw this up here. 1.20916 moles. That's helium. So it's 4.003 grams per mole. So we take that number, which is still in my calculator, well, kind of, times 4.003 equals 4. Now I'm going to round to 3 sig figs, 4.84 grams of helium. The 3A level version of this problem is they ask you to calculate N1. The 1A version is they're asking you to calculate the mass in grams that need to be added. Okay? So they make the problems more interesting. Any questions?